Okay, in this lecture, let us talk about the basic digital signals, I mean elementary digital signals. The most elementary signal is the impulse signal, okay. So it is denoted by del of n, and it is defined as 1. Del of n is defined as 1 for n is equal to 0. Okay, and 0 for n is not equal to 0. In other words, its diagram will be just one sample of amplitude 1 occurring at n equals 0. Its amplitude is 1, and the rest of the places the amplitude will be 0. Okay, so this is the plot of del of n. Okay, so it is 0 on either side, the right side also 0, the left side also it is 0, and this is the most elementary signal that one can think of. It is called a digital impulse. Okay, and if you compare with the analog impulse del of t, which is quite complicated, right? So del of t is analog impulse, and this del of n is digital impulse. Now, how is del of t defined? Del of t is defined as follows. Del of t exists exactly at t equals 0. Okay, t equals 0 only, and the amplitude at t equals 0 is infinitely large. Okay, it is infinitely large. Now if infinitely large, it doesn't mean anything, right? If I write like this, it doesn't mean anything. Okay, it does not give any meaning, right? So it is useless to define in this way. Okay, therefore the function will be useless for us. So del of t is defined as follows. Del of t is defined as you integrate right from 0 minus up to say some t, or 0 plus, and then this should be equal to 1. What does it mean? This gives the area. The area under the curve is 1. This creates a lot of problem because it is not a function in the ordinary sense. It is an unlimited function, right? The amplitude cannot be defined. It can be defined only in terms of area. Okay, so for del of t, amplitude cannot be defined. Okay, only area can be defined. However, there is no such problem in a digital impulse. Very simple, the amplitude is 1 at n equals 0. Okay, simply we can write the amplitude is 1, but you cannot write like this here, so it is infinity. Okay, so in digital pulse, the amplitude is 1 at n equals 0 and 0 everywhere else. Okay, that's it. It's very simple function. Okay, so a combination of such impulse functions give rise to a digital step function. So it is denoted by u of n, digital step function. So the digital step function is constructed with the help of digital impulse. Then now u of n is a signal which is 1 for n greater than or equal to 0 and 0 otherwise. So u of n is equal to 1, okay, which is 1 for n is greater than or equal to 0 and 0 otherwise. That means what? U of 0 is equal to 1, U of 1 is equal to 1, U of 2 is equal to 1, and so on and so forth. So if you want to plot this, then it looks like this. Keep on goes 0, 1, 2, 3. This is n axis. This is my U of n. Okay, this all are with amplitude of 1. Obviously, this U of n can be written in terms of del of n, and it is given by U of n is equal to summation of del of n minus k, where k is equal to 0 to infinity. Now put k is equal to 0, you get del of n. So del of n describes this guy. Okay, this is del of n. Okay, let me write down here. Put k is equal to 0. Okay, then put k is equal to 1, you will get a del of n minus 1. So this is denoted by del of n minus 1, and this one is del of n minus 2, and this one is del of n minus 3, and so on and so forth. Therefore, U of n is very simply related to del of n minus k. So del of n can also be related to U of n, that we will see now. Okay, so this is the relation between U of n and del of n. Now can I get back del of n from U of n? And the answer is yes. Okay, so your del of n is equal to U of n minus U of n minus 1. Okay, see, U of n will be like this, and U of n minus 1, 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 3, minus 2, minus 1, 0, then 1, 2, 3, like this. So this is my U of n minus 1. Subtract these two signals, then you will have only one signal when at n equals 0, and the rest of the places it is 0. Okay, so what is this? Del of n. So this del of n is given by U of n minus U of n minus 1. So that's how this del of n and U of n are related to each other. Okay, so this is the relation between del of n and U of n. So as a summary, I can write as follows. Summation of del of n minus k, where k is equal to 0 to infinity, is U of n. U of n, and del of n is equal to U of n minus U of n minus 1. Okay, and now any arbitrary sequence can also be expressed in terms of U of n and del of n. That is why these two signals are called elementary digital signals. Okay, so let's take an example. Suppose you have a sequence which starts from 0. Okay, okay, then 1 at n equals 1. Let's say my sequence is like this. When n equals 0, the value is 0. When n equals 1, its value is 1. And when n equals 2, it is 2. And n equals 3, it is 3. 1, 2, 3, like this. So it's look like a ramp signal like that. Okay, this is a finite length signal. So what is the length? It's 4. Okay, start count from 1, 2, 3, 4. So capital N is equal to 4 sequences. And the rest of the places it is not defined. I mean its value is 0. Okay, here I have considered the value at n equals 0 also. So I did not consider at minus 1, minus 2, then plus 4 and plus 5 and so on. I am considering only this length. Okay, so if you don't consider at n equals 0, then you might say its length is 3. Okay, now how do you write this signal? So this is my x of n. X of n is equal to, what is amplitude? 0, right? So 0 times del of n. And what is the amplitude here? 1. So plus 1 times 1 time unit delayed. So del of n minus 1. What is the amplitude here? 2. So 2 times del of n minus 2. Plus what is the amplitude here? 3. So 3 times del of n minus 3. Okay, therefore this is del of n minus 1 plus 2 times del of n minus 2 plus 3 times del of n minus 3. What is this? X of n. So x of n is expressed in terms of deltas, and x of n can also be expressed in terms of u of n. So how do you express? X of n is equal to in terms of u of n. Okay, so that is the next question. How can we express this? Okay, we can think in terms of figures. Let me plot 0, 1, 2, 3, 4 like this. This is my u of n, right? Now let me take another signal, u of n minus 4. Okay, so u of n minus 4, it starts from here and it keep on goes like this, and here the value is 0, and here also 0, here also 0 and 0 and 0 like this. 0, 1, 2, 3, 4, 5, 6 like that, and minus 1, minus 2, here also minus 1, minus 2. Now you subtract u of n minus 4 from u of n. What will you get? You will get a finite length sequence. 1, then 2, sorry, 0, 1, 2 and 3. This is what you will get. Okay, 0, 1, 2, 3. And what is this? U of n minus u of n minus 4. Okay, and this type of function is called gate function. Okay, this is called gate function. It exists from 0 to 3. Okay, now if you look at the original given signal, the amplitude is increasing proportionally. Okay, it is increasing proportionally. Okay, here n equals 0, n equals to 1, n equals 2, n equals 3. So the gate function is multiplied by n. So what you do is you multiply by n times u of n minus u of n minus 4. That's it. Okay, so because the amplitude is proportional to n, so you simply multiply by n. That's it. So any arbitrary signal can be expressed in terms of u of n and del of n. Okay, so there are a large number of problems in the textbook. Okay, so you can work it out. So SK Mitra. Simply we'll call it Mitra. That's it. Now one more sequence which is very often used okay, in digital signal processing, and that sequence is the so-called exponential sequence. Okay, and it is of the form a times alpha to the n. Okay, and alpha can be real, positive, or negative, or complex. It can be real, it can be positive, or it can be negative, or complex, whatever it is. Okay, in case if this guy starts from n equals 0, then what will happen? You will get a, then a times alpha, then a times alpha to the 2, then a times alpha to the 3, and so on and so forth. In case if it starts from n equals minus infinity, then it starts from a times alpha to the minus infinity, dot 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 dot, a times alpha to the minus 1, a, then a times alpha to the 1, a times alpha to the 2, and so on and so forth. Okay. Now if a times alpha to the n extends from n equals 0 to infinity, the way we assure this is multiply by u of n. In case my sequence is like this, then how do you write? A times alpha to the n, you simply multiply by u of n. That means it is a one-sided sequence. Okay, so therefore this is a right-sided sequence. Okay, starting from n equals 0. Now the question is a times alpha to the n u of n. Is it bounded? Okay. Yes, it is bounded provided that if magnitude of alpha is less than 1. Okay, magnitude of alpha is less than 1, then it will be a bounded sequence. Yes. If magnitude of alpha is greater than 1, it is not a bounded sequence. No, the answer is no, because it increases indefinitely to infinity. Okay, for example, let's say if alpha is equal to 0.5, then what will happen? You have a, let us take for a simplicity, let us take a is equal to 5, some amplitude 5 volts or something. So then what will happen? 5 times 0.5 whole to the 0, comma 5 times 0.5 whole to the 1, comma 5 times 0.5 whole to the 2, comma 5 times 0.5 whole to the 3, and so on and so forth. So this is going to be 5, then 5 times 0.5, 2.5, right? Then 5 times 0.25, so you multiply, you'll get a small number, 1.25 something, so it keep on goes. Okay, 1.25 and goes. So the values keep on reducing. See, it starts from 5, then half of that, again half of that, again half of that, it is decreasing. So therefore the sequence is bounded. In case if I take alpha is equal to 2, then what will happen? You get 5 times 2 to the 0, 5 times 2 to the 1, 5 times 2 to the 2, 5 times 2 to the 3, and so on and so forth. Now it is 5, 10, 20, 40, it keep on exponentially increasing. Okay, it's go on increasing on the on its value. Therefore the sequence is not bounded. Now instead of taking this type of sequence a times alpha to the n u of n, let me take a general sequence a times alpha to the n. That means what? The signal exists from minus infinity to plus infinity. I did not say where the signal starts, where the signal is starting. Okay, so this is my general signal. A times alpha to the n is a general signal. In such a case, how can we say whether the signal is bounded or unbounded? Okay, now the question is this bounded? Are there some conditions which will make it a bounded sequence? The answer is no. So it is not a bounded sequence. The reason is the magnitude of alpha is greater than 1, then what will happen? See, I can take only two conditions, either greater than 1 or alpha is less than 1. Okay. Suppose if I make alpha is equal to, in this case, alpha is equal to 0.5, then what will happen? In the left hand side, it goes on increasing and it is unbounded. If I take alpha is equal to 2, then what will happen? In the right hand side, it goes on increasing. Okay. So therefore, the sequence is unbounded sequence, whatever the value you take, irrespective of the alpha. Okay. Therefore, a times alpha to the n in general is unbounded irrespective of magnitude of alpha. Unbounded irrespective of magnitude of alpha. Okay, that means suppose in case if you put alpha is equal to in this expression, what will happen? It starts from a times alpha to the minus infinity, right? It keep on goes. So let me write down here, no problem. A times alpha to the n. Now let me take alpha is equal to 2. Then what will happen? A times 2 to the n. Now I substitute n is equal to infinity. Then a times 2 to the minus infinity goes a times 2 to the minus 2 comma a times 2 to the, let us forget a, okay, anyway this is constant, leave it up. Okay, I am not going to consider a here, simply consider only alpha. Minus 1, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3 and go on. Now what happens in this case? These all are bounded values. Okay, 1 by 2, 1 by 4, 1 by 2 to the infinity, these all are bounded values. But what about this side? It keep on increasing, right? So it is unbounded values. Okay, therefore whenever your mod of alpha is greater than 1, your right sided sequence is unbounded. In case if I make alpha mod of alpha less than 1, let's say 0.5, then what will happen? 0.5 whole to the n, then this is going to be 0.5 whole to the minus infinity, comma dot 0.5 minus 3, 0.5 whole to the minus 2, 0.5 1 comma 0.5 power 0 comma 0.5 power 1 comma 0.5 power 2 comma 0.5 power 3 comma and so on, right? Now this 1 by 0.5 to the infinity, right, this will be a very big value, and this also 1 by 0.5 whole to the 3, 1 by 0.5 whole squared, 1 by 0.5. For example, if you take this one, what will you get? This I can write 1 over 0.5 whole cube. Okay, so 1 by 0.5, the value is 2, right? 2 power 3, it is 8, and this is 4, and this is 2, and keep on goes. In the left hand side it is unbounded. So whenever the mod of alpha is less than 1, then the left side sequence is unbounded. What about the right hand side? It is bounded. Okay, you start from here 0.5, 1 by 0.5 comma, I'm sorry, this one will be 1, 0.5, 0.25, 0.125 and keep on goes. So this is bounded sequence. So one side it is bounded, in the other side it is unbounded. So right side sequence is bounded for alpha is less than 1. So that is why we said the a times alpha to the n is unbounded irrespective of magnitude of alpha. Now let us consider the most important signal in practice. Okay, see, the information is transmitted only by such signals is the sinusoidal signal. So let me write down a times cos of omega naught n plus some phase angle phi. Okay, so some phase, it doesn't matter. Okay, and whether you take a cos omega naught n or a sin of omega naught n some angle, phase angle phi, it doesn't matter. Now the question is it a bounded signal? Okay, so bounded refers to the amplitude, not the extent. Okay, so the maximum magnitude it can take is +1 and the minimum magnitude it can take is -1. So it cannot exceed plus or minus 1. Therefore it is a bounded signal, because the maximum value is a or and the minimum value is -a. Now the next question is it a periodic signal? Periodic. The answer is not unconditionally yes. Conditionally it is periodic. It may be periodic, it may be not periodic. Okay, may be periodic and may be non-periodic. We don't know. So depending on the situation we can say whether the signal is periodic or non-periodic. Okay, as we said, if it is to be periodic, then there must exist a quantity n, capital N, such that x of n plus capital N must be equal to x of n. So this is a condition for periodic, right? Let us test whether this a cos omega n plus phi is a periodic or not. So let me take a times cos of omega naught n plus phi. For the time being, let us forget about this a, its amplitude after all, right? So let x of n is equal to cos of omega naught n plus some phase angle phi. Now what is the left hand side? X of n plus capital N. So x of n plus capital N, replace n by small n by n plus capital N, that's it. Cos of omega naught n plus capital N plus some phase angle phi. Okay, now equation 1 and equation 2. 2 must be equal to 1. At what condition 2 must be equal to 1? Only when omega naught plus capital N is the integer multiple of 2 pi. Okay. Otherwise, no. Okay. So therefore 2 pi times some integer. Okay, let me call that integer as r, whole number. Okay, so here omega naught and n, and this n is also an integer, right? So in digital signal processing we said this n is an integer. Please remember that it cannot take any value other than integer. Therefore this capital N also integer and this r also integer. That means what? In other words, omega naught divided by 2 pi must be equal to r by n. The numerator also integer, the denominator also integer. That means what? ratio of two integers. In other words, omega by 2 pi must be ratio of two integers, or it should be a rational number. It must be a rational number, otherwise it is not periodic. Okay, for example, if I take a cos of 3n, what will happen now in this case? 3n plus 0 degree, phi equal to 0 degree, okay, phi equal to 0. Now compare this with your general signal a cos omega naught n plus phi. So instead of omega naught I have 3, omega naught is equal to 3. Okay, now the question is this condition, omega naught by 2 pi is a rational number. Okay, so 3 by 2 pi, now is it a rational number? Okay, somebody can say no, this pi is 22 by 7, then it is 3 by 2 times 22 and 7, so it is a ratio of two numbers. The numerator have 21 and the denominator have 44, so 21 by 44 is a rational number. No, the answer is wrong. Okay, because pi is not 20 by 22 over 7. Pi is not a rational number. Please remember that. Pi is not a rational number. Okay, approximately one can say that pi is 22 by 7. Okay, it is an infinite number of digits. Pi has infinite number of digits. In other words, while all analog sinusoidal signals are periodic, all periodic. Okay, but a digital sinusoidal signal may or may not be periodic. Periodic. So this is the important point one must remember. Next, let me take one example. Suppose I have three signals. Let's say x suffix 1 of n, comma x suffix 2 of n, comma x suffix 3 of n. And suppose each of them is periodic of period, let's say n1, and this is periodic with the period n2, and this is periodic with period n3. Now I am going to consider a signal, construct a signal, let me call x4 of n as a linear combination of these three signals. Okay, so alpha times x1 of n plus beta times x suffix 2 of n plus gamma times x suffix 3 of n. Now the question is it periodic? Is x4 of n periodic? Okay, so the answer is surely periodic. Yes, it is periodic, but the period is, let's say, n4, and this n4 is given by lowest common multiple of or least common multiple of n1, n2 and n3. Okay, let us assume that n1 is equal to 3 and n2 is equal to 5 and then n3 is equal to 12. Now you take the LCM of 3, 5, 12 and this is 60. So after 60 cycles, x1 of executes 20 periods. Okay, and after 60 cycles, x2 of n executes 12 cycles, like 60 by 3, 20 cycles. So x1 of n executes 20 cycles, then 60 by 5, 12 cycles. So after 60 cycles, x2 of n executes 12 cycles. 60 by 12 is equal to 5 cycles. So after 60 cycles, x3 of n executes 5 complete cycles. Okay, so this number 60 indicates each of them must have completed on integral number of cycles. See, this 20 is an integer, 12 is an integer and 5 is also an integer. Look at these guys. This all are integers, all are completing integer number of cycles, and therefore the combination is periodic with a period of 60. If the periods are prime numbers, it is simply product of their respective periods. For example, n1 is equal to 3 and n2 is equal to 5, then the period is simply 5 times 3, which is 15. But if they are not prime with respect to each other, then you have to take the LCM of these three numbers to get the total period. Okay. So let us go a little more into the interpretation of this signal. A times cos of omega n plus phi. So I did not put not here, okay. So I simply take omega n. Now how does one obtain such a signal, A cos omega n plus phi? Through the sampling process, as I said in the previous class, right? So you take analog signal, A cos, let me put a capital omega to indicate analog frequency, t times plus some arbitrary phase angle phi. Now how do you obtain this digital signal? From A cos omega t plus phi. Okay, now what you do is sample it at every capital T. Okay, every capital T you sample it and then you will get A times cos of omega n capital T plus some phase angle phi. Okay, and then give it to A to D converter. So the output of A to D converter is a digital signal, A cos omega n plus phi. That's it. Now what is omega? Small omega. How small omega is related to capital omega? Okay, so look at this guy, omega n. I'm sorry, once again. Here and this one. How are they related, these two guys? If you look at capital omega n capital T is equal to omega n. You can cancel this omega n and n both sides. Therefore, your small omega is equal to capital omega times capital T. And in the previous class I said this T is nothing but 1 over the sampling frequency, Fs. What is Fs? Sampling frequency. The rate at which you are taking the samples, sampling frequency. Therefore, I can write this omega divided by Fs, sampling frequency. Now this omega I can write as 2 pi f, and this f is the actual frequency of the analog signal. Actual frequency actual frequency of the analog signal in hertz. Okay, therefore I can write 2 pi f divided by fs, and you can also write this as follows, as 2 pi times 2 pi f divided by 2 pi fs. Okay, I am introducing 2 pi both in the numerator and in the denominator. So this I can write 2 pi times, this one is the numerator, it is capital omega, the denominator capital omega suffix s, sampling frequency. Okay, what is omega? Omega is angular frequency of the analog signal. Angular frequency of the analog signal. What is omega s? Angular frequency of the sampled signal. Okay, so therefore small omega can be written as 2 pi times capital omega divided by capital omega suffix s, or you can write 2 pi times f divided by fs. Okay, now you notice that capital omega was in radians per second. What is the unit of capital omega? Radians per second. Now what is the unit of small omega? That is the next question. Okay, it is dimensionless. The numerator also angular frequency, the denominator also angular frequency. If you cancel both, then the unit will disappear, and it is a dimensionless quantity, no dimension. Okay, small omega doesn't have any dimension. But how should we express small omega, right? Small omega is expressed in radians. Okay, see, as I said, small omega is a dimensionless number, but we express in radians. Why? After all, you know, omega is an angle after all, right? So after all, does radian have a dimension? No, this radians doesn't have a dimension. Okay, no dimension. What is radians? It is simply an arc divided by radius. Suppose if you have a circle like this, and this is my radian, and this radian is equal to arc length, let's say L1, and let's say this is R. So my radian is equal to L1 by R. L1 is measured in meters and R also measured in meters. If you cancel these two guys, then it is a dimensionless number. So radian is a dimensionless number. It doesn't have any dimension. Therefore, the small omega is the dimensionless quantity, and the small omega is termed as digital frequency. Okay, and it is measured in radians, and again this radian is a dimensionless quantity. Okay, and don't say the small omega unit is radians per second. Okay, in fact the proper way to is called normalized digital frequency, because you are normalizing with respect to fs. Okay, now let us recall what small omega is. Okay, small omega is equal to 2 pi times f divided by fs, and we shall soon see that in digital signal processing we cannot go beyond half the sampling frequency. Okay, I cannot increase this f beyond half the sampling frequency. Okay, so if you go beyond half the sampling frequency, then there is a distortion. So f cannot be greater than half the sampling frequency by 2. Okay, if this condition occurs, then distortion will occur. Okay, therefore your f must be strictly less than or equal to fs by 2. Therefore the maximum value f can take is 2 times of fs by 2. Okay, so this f can take maximum value that f can take is fs by 2. It's a very important point, that's why I'm writing all these things. It cannot take more than fs by 2, therefore substitute here. So maximum, let me write out, omega suffix maximum is equal to 2 pi times f maximum divided by fs. 2 pi times f maximum is fs over by 2 divided by fs. Fs will get cancelled. 2 pi by 2, therefore pi. So the maximum value of normalized digital frequency is pi. Okay, therefore the range of normalized digital frequency lies between 0 to pi. And for a real signal, whatever positive frequencies, there must exist a negative frequency also, and therefore the actual range of small omega is from minus pi to plus pi. So this is the range of omega for a real signal, because for real signal it always comes with pair, right, positive and negative. And this range minus pi to plus pi is called a baseband, or sometimes people will call band of vision. So this is the beauty of digital signal processing. So band of vision means that where you have to focus your attention in DSP. So this is a very important advantage of digital signal processing. Okay, so this is fortunate that our range of vision is minus pi to plus pi. See, in the analog frequency, the frequency ranges from minus infinity to plus infinity. Okay, so but here in omega the range is limited, minus pi to plus pi. So this is my range of vision. Range of vision is limited in digital, but here range of vision is not limited. You have to look from minus infinity to plus infinity. Not limited. Okay, in digital it is only limited between 0 and pi if you want to plot the magnitude and so phase and so on and so forth. So no need to plot from minus infinity to plus infinity. You have to plot only from minus pi to plus pi, that is enough in your digital domain. But in the analog domain you have to look at from minus infinity to plus infinity. Okay, you have to go from minus infinity to plus infinity in analog. In digital, this is the advantage. We don't have to compute beyond pi, and we don't have to compute beyond minus pi. But you must remember that small omega is normalized frequency. It is not the frequency in radians per second. It is in radians. Okay, don't say the small omega is radians per second. Answer is wrong. Okay, so omega is only radians. So we will come back to why the restriction of EF a little later. Now digital signals are subject to some operations that we will see now. Okay, so let us talk about some operations on sequences. So what are the operations that one can do on digital signals? So the first operation that we are going to look at is multiplication. Okay, if a sequence x of n is multiplied by another sequence, let's say y of n, to form a new sequence. Let's say that sequence is called w of n. Okay, so it means that the corresponding samples are multiplied, right? Suppose you substitute n equals 0, then w of 0 is equal to x of 0 times y of 0. Substitute n equals 1, w of 1 is equal to x of 1 times y of 1, and so on and so forth. So substitute n is equal to I, w of I is equal to x of I times y of I. Therefore, the ith signal in w is obtained by ith signal of x and ith signal of y. Okay, so ith signal in w is obtained by ith signal in x and ith signal in y. Okay, now let us indicate this operation pictorially. X of n, you put a circle, and within the circle you put a cross like this. It indicates multiplication operation. And here this is y of n and w of n, you put an arrow mark. And this multiplication is a non-linear operation. You can verify this. Okay, so the multiplication operation is not a linear operation, it is a non-linear operation. Note the point, non-linear operation. However, as we shall see later, in FAR filtering we do use multiplication of two sequences. Okay, that is the only place where we use this multiplication operation, because we are mostly interested in linear operation, okay, linear systems. So but this is non-linear, but still we use in certain places. That is in FIR, finite impulse response filters. Okay, so we do use multiplication of two sequences. We multiply the given sequence by what is called a window function, and there does exist cases where the multiplication has to be resorted to. And one more point, suppose two sequences are not of the same length, then what we have to do is we need to add some zeros. Suppose x of n has a length of 3 and y of n has a length of 7. Then how do you multiply? Because the fourth sample in x of n is not there, and fifth is not there, sixth is not there, and seventh is not there. So what you do is you pad zeros. Pad zeros in x of n before doing any operation to make any operation. So you make the two length identical by adding zeros to the sequence which has less number of samples. Okay, for example, let's say x of n is equal to 2, 4, 7, 2, 4, 5 like this, and you put an enter. Y of n is equal to -3, 2, 5, 4, 3, 2 like this. Like this. So what is the length here? 1, 2, 3, 4, 5, 6, 7. The length is 7 here. Okay. And here what is the length here? 3. In that case you cannot multiply, right? Term by term you can multiply this and that, this and that, this and that you can multiply. This and that you can multiply. Term by term you can multiply. But beyond that what will you do? So in that case what you do? You pad some zeros. How do you pad it? X of n is equal to 2, 4, 5 and pad another 4 zeros. Okay. 4 zeros. So this operation is called padding, adding zeros at the end. And then your original sequence y of n is -3, 2, 5, 4, 3, 2, 8. Now both are of the same length, then you can do the multiplication. Okay, and next we will talk about addition or subtraction. Okay, when you add x of n to y of n, that is add or subtract, then the corresponding samples are added to form the new sequence. Let me call the new sequence w of n. So it is x of n plus y of n, or you can write x of n minus y of n, or y of n minus x of n, whatever it is, doesn't matter. Okay, so we use the summation symbol for addition. You put a circle, summation symbol, this is x of n, and this is y of n, and this is w of n. Okay, in case if you want to, this is addition. If you want to subtract, then you put the same, summation symbol, but here you put the minus. This minus indicates you are subtracting. For addition, no need to put any plus symbol, simply put the arrow mark, that is enough. So this minus indicates you are doing the subtraction operation. So therefore w of n is equal to x of n minus y of n, that's it. Okay, but here sign will be avoided. Okay, so negative sign means simply that y of n is to be multiplied by minus 1. Okay, minus 1 is not a multiplier, it is simply changing the sign bit of the binary number. Okay, so this and all you will be studying in your digital electronics. So one more point that needs your attention is, in digital signal processing, as you know, in digital hardware, we cannot add more than 2 numbers at a time. Okay, if somebody writes like this is wrong. At a time you can add only 2 signals or 2 numbers. Okay, you cannot write like this, x of n, y of n, and z of n equal to w of n. You should not write like that. Okay, this is wrong. Okay, then in case, how do you write this guy? What you do is, you put one adder, x of n, y of n, then you put one more adder, you put z of n here, and then you'll get your w of n. Okay, because as we know, in accumulator, in digital hardware, there is something called accumulator. In your microprocessor or in your digital electronics, you'll be studying something called accumulator. So in accumulator, we feed numbers in sequence and it accumulates. Okay, it adds the number and replaces the storage by the result, then takes another number and adds, and so on and so forth. So this is the discipline we must exercise. In other words, whenever we want to add 3 numbers, for example 3 signals, then we shall use 2 summer here, summer 1 and summer 2, 2 summers. 2 summers we need to use it. 2 summers we need to use it to indicate the steps to add the 3 signals. Okay, what is the next point that I would like to say? Yes, and then in multiplication also there are 2 types of multiplication. I forgot to mention that. So one is scalar multiplication, and second one is 2 signals multiplication. Okay, so this we already discussed, 2 signal multiplication. If you look at here, so this one, normal multiplication. Okay, x of n multiplied by y of n. But when I say scalar multiplication, then x of n is multiplied by a number, okay, some alpha. Therefore your output to y of n is equal to alpha times x of n. All sample values are multiplied by this constant alpha. So, okay, so we put alpha inside the circle. So this is a scalar multiplication, and it is not a multiplication of sequences. Okay, it is a multiplication of a number. and the next one is time reversal operation. Okay, so let's say x of n is given, and if the index is reversed down, then you will find up x of minus 1. It means flip over. Okay, so x of n flip over, you'll get a x of minus n. This is called a time reverse operation. In case if x of n is right sided sequence, then this guide will be left sided sequence, and vice versa. Okay, for example u of n, then it becomes u of minus n. That is your time reversed sequence. See, u of n starts from n equals 0, 1, 2 and so on, and this guy starts from n equals 0 and then minus 1 and then minus 2 and so on and so forth. So this is u of minus n and this is u of n. Okay, it is a right sided sequence, it is the left sided sequence. Okay, so the definition of u of n is it starts at n equals 0. Okay, and u of minus n is it starts at n equals 0 and goes keep on to minus n. Suppose if I take the sum of u of n plus u of minus n, what will you get? Okay, so you'll get u of n plus u of minus n is equal to 1 everywhere except n is not equals 0, and the amplitude is 2 when n equals 0. You can work out. Okay, you will get the answer. Okay, so for example, what is this u of n? 0, minus 1, minus 2, minus 3, 0, 1, 2, 3, and this is u of minus 1. If you add these two guys, what will you get? You will get like this, but here the amplitude is 2 at n equals 0. Here one amplitude is 1 and here also 1. If you add these two guys, you will get 2. Okay, and then here 0, 0, 0, and here also 0, 0, 0, 0 plus 1, 1, 0 plus 1, 1, here 0, and here the value is 1, so it is again 1, and here it is 2, 1 plus 1, 2, and then this value is 1 and this value is 0, so you will get a 1 and 1 and 1 and so on. Therefore, everywhere it is 1 except at n equals 0 it is 2. That's why this u of n plus u of minus n is equal to 2 when n equals 0 and 1 when n equals 1, when n equals not equal to 0. Or in other words, you can write u of n plus u of minus n is equal to 1 plus del of n. That's it. For all n. Now, in case if I have u of n plus u of minus n minus 1, what is the answer? You can check it out. Okay, and this is equal to 1. Check. Okay, check. This is the answer, 1. Okay, so u of minus 1, u of minus n minus 1 has a special significance. Okay, we shall come back to this a little later about this guy. The next operation is delay. Now delay will be represented by a special symbol z to the minus 1, which we shall discuss later the significance of this, but it simply means that if you have x of n as the input, the output will be x of n minus 1. You give it to the delay z to the minus n, and the output will be x of n minus 1. Okay, this is delay, 1 unit delay. In terms of hardware realization, it is simply delay, one sample delay. It is simply one sample delay. So in terms of software, in terms of your program, it means retrieving the immediate past sample. Retrieving the immediate past sample. Okay, so if you require x of n minus 1, you retrieve it, okay, you bring it back. So this process is symbolically represented by a block like this, whose transfer function is z to the minus n. For example, if you recover x of capital N unit of delay, then you will have to feed x of n, okay, to a chain of such delays, z to the minus 1, z to the minus 1, dot dot dot, like this. So here x of n minus capital N. So in this point you will get x of n minus 1, in this point you will get x of n minus 2, and so on and so forth. Okay, so there is no way we get a z to the minus n directly. Okay, simply you cannot put like this, z to the minus n and x of n minus capital N. This is wrong. Okay, don't put put like this. I think this concludes our discussion on digital signal. Okay, so the next lecture we will discuss digital systems. Okay, so we will talk about digital systems. So how digital signals are handled by the digital systems. So in the next lecture we are going to talk about digital systems. Okay, so let me stop at this point. Thank you very much.